Hello, everyone. Welcome to today's live broadcast, Introduction to the new USP 787 Subvisible Particulate Matter and Therapeutic Protein Injections. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots and sponsored by Beckman Coulter Life Sciences. Beckman Coulter Life Sciences is the premier global supplier of instruments for particle counting and particle characterization in the nanometer, subvisible, and visible ranges. To support its customers, the Beckman Coulter brands, Met1, Hayek, and Coulter, are backed by a global service organization. For more information, please visit the Beckman Coulter Particle Counting and Characterization website, www.particle.com. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you have any technical problems viewing or hearing this presentation, please click on the support button at the top right of your presentation window or submit your problem through the green Q&A button lower left. I would now like to introduce today's speaker, Joe Gecsey. Joe has been involved with particle counters and characterization since 1984. While his degree in electronic engineering has given him a good insight into the design of these instruments, it is his continuous involvement in the real-life applications of particle counters in a broad range of industries that has enabled him to relate to the users and to promote the efficient application of compendial methods. Joe has participated in a number of standards organizations and activities, including the ASTM Committee on Testing Stents and the IESP Committee on Calibration Methods. He recently participated in the ISO TC 209 Working Group 1 Committee for the revision of the ISO 14644-1 Cleanroom Classification Standard, one of the two Americans on that committee. He is also a member of the ISO TC 24 group working on standards and methods for particle counters and particle characterization. Joe is based in the United States in the beautiful mountains of Southern Oregon. I will now turn it over to Joe Gecsey for his presentation.
Yes, thanks, Judy. Good morning, and thank you for joining us. I want to cover the most recent introduction of a particle counting method from the American USP called USP 787, and it addresses some of the issues that people have had concerning the sampling of proteins in the final product mode. So we'll cover a little bit of the history of the injectable product testing, as well as kind of define some of the terms that are used, visible, subvisible, why 787 came about, why the previous methods were not quite appropriate, how it's different from the 788, a lot of people are familiar with, and then also comparing it to the Journal Information Chapter 1787, and looking to follow through with alternate methods and technologies that could be used for the examination of proteins. So first, a bit of history. Well, injectables have been tested for quite a while in various methods, certainly in the earlier days with microscopes, then followed with the concerns or the methods of optical particle counting. The main concern, though, initially was any objects that might affect the human bloodstream. And the main concern there is that capillaries are quite small. They're down in the 10 micron or so range to allow red blood cells of about 5 to 7 microns to pass through. And so anything that might be introduced into the bloodstream that would be 10 microns or larger would then potentially block or occlude the capillaries, and of course that's not a positive thing for people's health. So there was a lot of focus then done on the restriction and control of 10 micron larger particles. So that's where a lot of the original design was, and of course ultimately the concern is someone ultimately gets your therapy, the injection, and in many cases the person has already compromised health, so if you put something directly in the bloodstream, that's not beneficial, it's not has the full therapy that is intended, well, that's not the best thing for their recovery. So that's been a lot of the focus. How do you keep unwanted, insoluble chunks of material out of the injections? And those could be regular injections you might get in the doctor's office, or it could be in a hospital setting with an IV drip. Either of those are introducing materials into the bloodstream directly. And those are the greatest concerns, the greatest focus of the regulatory agencies. But any kind of injection into the body, of course, has some risk and some constraints. Major focus, of course, has been towards the actual introduction directly into the bloodstream. So, you know, the FDA, the American FDA, talks about that as contamination or adulteration, partly because it's something that wasn't intended, it was introduced, but certainly because of the concerns with the blockage of blood vessels, particular capillaries. All kinds of things have been found in history in IVs. Today, of course, filtering methods and control methods are much more strict and carefully observed than in times past, but all forms of materials coming from the process and from the environment around the process steps, how the containers are being filled and so forth, can potentially introduce contamination. So these have all been the focus of some of the concerns with the regulatory agencies and some of the controls they've put in place. The primary method for looking at the final product has been, since about the 1960s, the optical particle counter, light obscuration, or LO method. And there has been a unique effort in this industry to harmonize the methods from the U.S., from Europe, from Japan, from Korea, and now even with China, trying to come with a consistent method globally for this critical test of injectable materials. The secondary method is the good old trusty optical microscope. And light microscopes are wonderful, but they are very slow. They're somewhat dependent on the skill of the observer, and also, of course, over time, in a day over 8 hours looking through a microscope, probably the ability to analyze is not as good as when one was fresh at the very beginning. So the optical particle counter has served very well in the industry to provide a consistent, repeatable method for determination of particles in injectable materials. So we have these Pharmacopeia methods, the USP 788, the European EP 20919, Japanese 607, the Korean 51, and so forth, that all basically have the same method, the same steps to test it, and the same limits. Somewhat more recently, the Chinese method was introduced, and it's notable mainly because it also discussed biologics. This was kind of the first discussion that was brought out, and it was introduced in 2010, and it's strictly focused on intravenous injections, and they did make, as I said, a separate chapter. Now, the wording turns out to be the same at the moment, but it kind of laid the ground for looking at biologics in a different way. And the USP has been engaged for a number of years already in discussions with the industry and a focus towards trying to find a better method to deal with biologics, in particular with protein solutions. So when we talk about these various methods, there's been certainly a lot of focus recently with USP 790 and similar methods for visible particles, so there's a lot of discussion about that. This particular chapter has to do with subvisible, and so how does that kind of define? What does that mean? Well, in a lot of cases, people think of the ability of the human eye to see small objects, and it kind of gets to a limit down around 35 to 50 microns. That's about the best the unaided human eye can do, and so most people tend to think of that as the constraints of visible, subvisible. It turns out, though, in the compendial methods, in the USP in particular, they speak of visible starting at about 100 microns, and subvisible as being that range a couple of decades below that, from about 1 to 2 microns up to 100 microns. And then below that, we have submicron or nanometer below the 1 micron range. So Subvisible, as this chapter applies, is mainly focused in that range from 1 up to 100 microns in size. And if we look at the current limits that have been posted for 10 and 25 microns, that fits into this subvisible range. So we're looking for things that the human eye normally cannot see, but are of concern once they get into the body. So why have a new chapter? What's the focus for 787? Well, fundamentally, it's addressing the needs, particularly of the production and testing of protein-based therapeutics. And it's looking at the final dose and packaging of it. It allows the use of smaller test volumes, which is kind of the critical point for a lot of people in the industry. The amount of material needed to test under 788 was significant, typically 25 milliliters, and that can be quite an expensive test to execute at that volume. Also, you can use under 787 smaller amounts of material to carry out the analysis. So no longer does it have to be a 5 milliliter pull, it can be a smaller amount. And this again is a cost savings and also a nod to the fact that most of the therapeutic doses for protein-based materials are relatively small. We're talking often less even than 1 milliliter for an injection. It also speaks then about an inherent form of particulate matter that had not been really brought to the fore before, as you'll see. And it goes through and, of course, describes a bit more the preparation and test, and those are different from the existing 788 method for general injectables. And, of course, it defines the maximum limits of the particle burden for therapeutics. Again, please note that this is focused on proteins. It is for protein-based therapeutics, does not generally apply to all forms of injectables. So what is it saying? Well, first off, the primary method is still the light obscuration device. Light obscuration sensors have been used again in this methodology since the 1960s, and that continues to be the primary method used. Very repeatable, and that's one of the values. Very fast, very repeatable. Of course, still, there's some types of materials that are difficult to test in that manner, so light microscopy is offered as a secondary method should the primary method based on light obscuration not be appropriate for a certain material. There's still a minimum number of test pulls for aliquots needed, but they can be now much smaller, as we'll see. Sizes of interest, still 10 and 25 microns. And the limits look the same, really. So we'll see there's a slight variation when we look at the large volume, but basically you're looking at limits of 600 for 25 micron, 6,000 for 10 micron in small volume, and large volume 25 at 10 micron, 3 per ml at 25 micron. So same limits as 788. But again, the problem with 788 for some of this very expensive material is the cost of the test under 788 and some of the ways that the handling of that test material was done is not appropriate for proteins, as we'll see. So 787's been introduced. It's been effective under USP from August 1st in 2014. And it looks a little bit like, as I said, 788. However, the size of the aliquot can be down to 0.2 milliliters. You can also then do environment tests based more on the actual size of samples you'll be taking, and those could be certainly less than the 10 mil test for environments that is in the current 788 method. So it's basically set as counts per ml for the environment test. So what are the challenges? Why have this methodology? What's the value? Well, certainly all forms of handling can change protein-based material. It likes to wrap around itself or other items. So silicon oil, beads, anything else can cause it to form other bodies besides the primary material. So a lot of agitation can cause aggregation of the product. Heat, light can affect it more readily. Various contaminants, as I said, silicon oil or little bits of material can form seeds that the protein then wraps around. The various types of containers and methods have an effect on it, more so than on regular small molecule therapeutic doses. Shear forces can affect this much more readily. The way you pump material, feed it into various parts of the process can be significant. The real key concern for most of the regulatory agencies is concern with the aggregation, the forming of different constructions of the protein rather than the original intended protein material. And again, this can happen very easily. And in the body, it can change the reaction. It can either create a immediate immune reaction, or it may trigger over time immunogenicity that slowly makes the therapeutic effect of a particular medicine much less so over time. So the concern then is, how do we monitor that? Certainly in the process you look at how to control it, but even after that, how do you deal with it? Because again, you're changing the native form, and maybe you're getting proteins that wrap around themselves, so it's homogeneous, it's the same material, or it might be wrapped around something else, a bit of glass, a bit of silicon oil, something else foreign wraps around it, so it makes a heterogeneous aggregate in the process. But any of these are really something that you want to minimize. It's hard to avoid it entirely, but certainly minimize as much as possible. As I mentioned before, we discussed the inherent type of contamination, and it's a new kind of third point that's more prominent now. It's always been of some concern, but now with proteins much more so. So the three different types are extrinsic, intrinsic, and inherent. We'll touch on each one of these. The first two, extrinsic and intrinsic, are the ones that have been most commonly focused. Extrinsic is something that you really can't relate to the normal process. And it might be cellulose, it might be something from outside in the room, gypsum or paper that should not be there at all in the process and is not expected at all. Intrinsic is looking at things that, well, okay, you don't want them, but could be results of the process. It might be bits of metal from a filling needle that scraped the glass a little bit, or it might be a bit of glass that is left in the container due to improper washing, or some other form of something related to the process. So that's one form, again, the second form of contamination that could occur. This third form, the inherent, is somewhat of a new term, but again has been discussed in previous times, but without the same kind of focus or spotlight, you could say, that is brought about when discussing proteins. And often then it really relates to material reforming itself in one way or another, as an aggregate, or even maybe disassociating into some other quote, broken form, you could say, of the original protein. From 787, which is the informational chapter we'll touch on in a moment, in 1787, it speaks about materials that are expected from the drug substance and thus represent a potentially acceptable characteristic of the product. And of course, it's potentially acceptable. Doesn't mean that it's good, or in terms of long-term therapy, might not trigger immunogenicity or some other reaction that is not therapeutic. So inherent, not contamination. So we often talk about contamination thinking about something external. Here we're thinking about something that is, in a sense, a creation of the material itself. And proteins easily wrap around themselves. So it's a shift from the native form. So what we're worried about is different structures, dimers, oligomers, other kinds of protein complexes that we really would prefer not to be there. And in small quantities, probably not a problem. In larger quantities, can be much more so. So there's a focus in 787 more on both the sample and system preparation than before with more simple small molecule preparations. So how is that a bit different? Well, when you look at 788, it says, please, mix well, sonicate, and so forth. So you invert slowly, try not to introduce gas. You don't want to shake it, but you invert slowly, and you sonicate the material to kind of break things up and change it. However, that's a concern with the proteins. What you're trying to do is not add entrained gas by agitating too much. You don't want to shake it. Sonication is a form of shaking, you might say, for proteins. So it's agitations adding kinetic energy into the solution or suspension, and then changes easily then the material. So that's problematic. So how can you deal with entrained gas? There might be some in the material, and as you analyze it, it might bring microbubbles out. Well, a light vacuum seems to be a good way to deal with that. And so it talks about using a light vacuum. You might use the old-fashioned bell jar, or maybe a more current desiccation chamber, something where you can draw a light vacuum on the material and bring any of the entrained gas out of solution, and therefore minimize any analytical error due to microbubbles. So degassing is a general term used. And so eliminating gas bubbles, and as it's spoken about in 787, talks about then a light vacuum, about 75 torr. Very clearly states sonication should be avoided. So again, a fairly different approach to working with material for proteins. In 788, they talk about inverting, gently inverting the packaging, whether it's a vial or whatever material you're working with. And then it says, to sonicate in 788. Here in 787, very clearly a different direction. And they say very directly, inversion to mix the product fluid is not recommended at any time. So again, different handling for this protein-based material. Dilution. A lot of materials are thick, or maybe highly concentrated, or both. And in some cases, you cannot introduce it easily into a light obscuration system due to those factors. So maybe dilution is necessary. Under 787, they do discuss that, and they say that the effort to dilute needs to be carefully done. There's quite a bit of discussion of that in the informational chapter 2 in 1787, because by diluting a protein-based material, you may cause dissociation or potentially aggregation, just depending on the type of formula and various other aspects of the material. So dilution is allowed, but it must be carefully done. What about the overall system and setup to execute the system? Well, normally when you're working with light obscuration counters, or actually any other counter, you do two things. First off, you want to start out and say, is everything running right? So in the beginning, before you do a series of tests, maybe at the beginning of the day or beginning of a new shift or new operator, you run a couple of test solutions. You run a blank, something that tells you, yes, it will effectively read a very, very low count, if not zero. And then you give it some kind of a challenge with a known value of counts in the approximate range of interest. And you might do those then in the beginning of morning. It might be also you only use the system once a week. Okay, before you start that process, you do a couple of these verification steps. It's not a calibration, but it's a check. It's a health check for the system to give you confidence that it is going to function correctly and the results can be considered accurate. In 787, system preparation is stated in the same form, although for the test of materials, they talk about system suitability. And they recommend using the USP PCRS, and that stands for Particle Count Reference Standard. So it's a material of a known quantity at a certain size, typically then 15 microns and about 3,800 counts per milliliter. or the system says the method says you can use an alternate. So you might find certainly commercial material available that would give you the same basic level of confidence that yes, if you present a certain level of material, the system will read it. If you give it a 1,000 counts per ml material, it will read approximately 1,000 counts as you begin the process, and therefore you have confidence that whatever might be in your test solution will be accurately represented. So again, 787, a little bit different, and you can run smaller amounts of material. The current systems today allow you to run down accurately to about 0.2 mLs of material on each pull. You still need 4 pulls, so that could be then about 0.8 of material. Typically, it would be about 1 milliliter of material to pull 0.8 out of in a system. When we go through all this and we evaluate the results, how do we look at that? Well, again, the limits are the same as in 788, with the exception that for large volumes, it needs to also meet a container test. Well, this is a bit new. There was certainly a container test before for any materials under 25 mLs, under 100 mLs, but now greater than 100 needs to pass a container test too. So there could be a, let's say, a 1 liter, a 1,000 milliliter IV solution bag, and you've created that or loaded it with a protein-based material. That whole container then needs to be tested in terms of counts per ml, and also in terms of a total container, maximum amount of contaminant recorded at 10 microns cannot exceed 6,000 counts, and at 25 microns cannot exceed 600 counts. So this is the variation, you could say, on the numbers. Otherwise, you're kind of following 788, especially for small containers. So let's talk a little bit about light obscuration, a little bit about the methods, very briefly. It may be something you're very familiar with, it may not, but light obscuration has been around, as I said, for quite a few number of years, and it's also sometimes been referred to as light extinction or light blocking. And it gives good information starting from about 1 micron up through several hundred microns, depends on the exact design of sensor, but somewhere in that range, it really gives good results for any kind of foreign material or object in a liquid. One of the good things analytically about this is, first off, it's very quick. The answer is given really in seconds. There's no need to add chemicals, so it's not an analytical process where you have to stain something or do some other analytical step preceding it. There really aren't any other consumables, and most importantly, the results are very repeatable using the method and reproducible between different machines, because in many cases a facility might have more than one instrument, and of course you want the instruments to record the same results. The important thing to realize is that we're dealing with very irregular forms of material, and we talk about particles with a certain size. We use one dimension to record these. That's an interesting aspect when most of these particles, in fact, are very much three-dimensional. So we're going to sample this. What do? Well, first off, we have a pathway that the liquid flows through, so we have a channel. And then on each side of this channel, we put a couple of windows. We put a light source. Typically today, it's a laser diode. We shine a light through to a detector on the opposite side, and we look for anything that comes between and modifies the beam, creates shadows, you could say, on the detector. So the detector is normally sitting there with bright light shining on it, so it has a high level in its normal uninterrupted state. And then when you introduce a particle into the system, it obscures or blocks it. It creates a shadow on the detector. It may not totally block it, unless it's a very, very large particle, but in most cases it simply creates a shadow passing over the surface, and that shadow diminishes the light, and therefore we can detect it. And the larger the particle, the greater the diminishment of light, the bigger the shadow. So we can tell A, the quantity, and B, the size of that object as it passes through, and we correlate that or relate it to calibration materials. So again, larger the particle, the more significant signal we get from the particle in the channel. This is an optical instrument, so we use light to detect it. We need to push or pull fluid through the sensor. Depending on the design, from light scattering through light obscuration, optical particle counters can see down into the nanometer range and fairly large size up to several hundred, or if not several thousand microns, but that depends on the design of the sensor. It does count particles individually. Okay, that's one of the key things about particle counters as a design. They're really looking specifically at events one at a time within reasonable concentration. We cannot tell you the composition. We can't say, that's a bit of aluminum, or that's a bacterium, or something. But the results are immediate, and we can quickly quantify the material that might be in suspension in a particular test fluid. Common design, the HIAC 9703, is tuned specifically for the pharmaceutical needs and works for both 788 and 787 types of analysis. So again, what we're dealing with is a particle counter, a numerator. So we're telling you how many particles are seen at a certain size or within a range. Typically in the ones used for this purpose for 787 would be from roughly 1 micron up to perhaps 600. The results are, it says here minutes, but almost seconds. You're getting results very quickly. And we're enumerating, so we're counting, we're saying the size, but we can't tell you what it is with just this simple analysis. So we can't give you some of the things you often might want to know about particles: morphology, the color, the mass, the composition. No, this machine is basically giving you quantification or counts. So it is a counter. As I said, the unique thing in this world is that really we're dealing with three-dimensional objects in most cases in the real world. So we have objects that are definitely not round or spherical. They're whatever might be encountered. Bits of glass, bits of aluminum, fibers from garments. All these types of things might be present, hopefully not, but have been certainly found in injectables. Well, people have struggled with this for a number of years. In fact, it goes back several hundred years with light microscopy. How can you describe an irregular shaped object? So various methods have been devised. The largest dimension, or ferret's diameter, have been really commonly used in light microscopy to, in a sense, reduce a three-dimensional object to a description using one dimension. But you could say, well, that's not very accurate. But also, it would take a lot more time, especially if you have a good number of objects, to try to quantify a large number of objects in 3 dimensions. So this is a form of shorthand that gives us a pretty good picture of what's in the particular fluid, and if there's too many according to a standard. So in this case, we're looking at injectable pharmaceuticals. We want to know that it's below a certain limit. Ideally, you'd say, gee, if it's injectable, I'd like it to be 0. And that's certainly a good target, but it's also usually a very expensive one to achieve. So it has been found over years that the limits that have been used here, 6,000 per container for at 10 micron and 600 for container at 25 micron, are effective enough controls. Human body can deal with that in a reasonable way. Well, when we use a light obscuration counter, we're doing something a little different. As I said, we're kind of looking at shadows, and we're taking that area that is projected onto our detector and relating it to an equivalent spherical size. So when we talk about the size given by a light obscuration sensor, we're looking at a surface area. We're looking at an area value for the equivalence to describe it with a single dimension. If you go to the USP in 776, they discuss optical microscopy, and they talk about some of these methods. And when you look at those and you try to set forward then what it would be for that object using ferrets, so we say, okay, ferret's diameter, well, it's about that length in equivalent. And then we go and we look at the projected area, excuse me, the maximum horizontal, and then we also look at projected area. Martins, we get different values. So it's very important to realize that when you use these various methods, be it light microscopy or light obscuration or Coulter counter, as we're discussing a little bit later, all these will give, in a sense, slightly different variations on the size value. And this historically has been the reality, even using light microscopy for several hundred years. So it's important to really, when you give a statement about a method and its results, that you clearly state the method. I used the light microscope. I used light obscuration. I used the Coulter counter. All of these would give slightly different results, and they need to be indicated that way. And that's actually some of the advice we find in 1787. So again, you'll end up then with different actual dimensions, so to speak, diameters given by these different methods. So in 1787, they discuss that, and they say, you know, size is very important. Size is a good attribute or something to know about an object in the fluid. So it says size is a particle attribute that has been monitored historically and remains a primary descriptor. Subvisible particles could also be described as aggregates or particles between 1 and 100 microns based on, and it gives several of them, but the ones we're going to focus on are ECD, so a new kind of terminology thrown out there, ECD, the equivalent circular diameter, which is what you'd find from light obscuration, a longest chord, which is commonly what you might find in light microscopy, or ESD, the equivalent spherical diameter, which is what you would find in the Coulter method. All of these are valid. None of them are, quote, wrong. But again, we're trying to bend the rules here a bit. We're saying we're going to take a three-dimensional object and describe it with one dimension. Well, all of these will have then slightly different variations on the value given. So at the end, in 1787, they make also this comment, with any size measurement, the method used should be specified. So when we compare the optical particle counter to a microscope, when we size that with a microscope, it gets a bit subjective. We find that it depends on the particular type of microscope, it depends on the operator, it depends on how tired the operator is, and so forth. When you use an electronic method, it's much more consistent and repeatable, and of course, between instruments, reproducible. The particle orientation movement is something that electronics has to deal with also. It's not sitting there as a flat object on a slide in a microscope. So long particles can often be a little more of a challenge, but generally you don't have that many fibers. When we speak of long particles, I think mainly of fibers like from garments or other sources that would be in the fluid. And we have to think about calibration. How do we relate then this electronic response to the real world, to sizes of spherical objects? So we want that to be consistent. We want repeatability. And that's one of the things that the electronic methods for particle counting definitely offer, is repeatability. So we're reporting a size, but we're using optics in the case of light obscuration, and you'll find differences then to other methods. But we do calibrate. We use the calibration material that is commercially available and are traceable to national organizations. In the case of the United States, we talk about them as being traceable to NIST, which is the National Institute of Standards and Technology. And these are very, very beautiful, precise microspheres. And so we have a quantity of those. We certainly are looking for consistency in size. We introduce that to the machine. We record the response. And that becomes a calibration based on multiple introductions of sizes. So we create a calibration curve or response curve over a range of sizes of interest or the instrument's capability. Again, for light obscuration, that's typically something on the order of 1 micron up to 3, 4, 500, 600 microns. So these types of instruments then are focused to that purpose, and basically combines a sensor to actually do the detection, some form of a sampling system to meter a volume, because again, we're talking about counts per unit volume. So we want to know that that's an accurate volume. So we have a metering system. Commonly, a syringe drawing system is used to aspirate sample out of a vial or the container. And then you have some form of representation of the information, software used, ideally with the compendial methods built into them to allow the consistent method, and also that is something that in terms of electronics is very well defined and developed. So in the U.S. and many cases around the world, we refer to the 21 CFR Part 11 methods to control access, to control the methods and consistency of software response. So you want all those aspects in a system. In terms of dealing with proteins, some of the modifications that have been put into place are ways to deal with very, very small volumes, or maybe even material in a centrifuge or pointed tube, something that's kind of hard to balance on a flat stand. So in order to make that more effective, we've designed into the instrument ways to handle very, very small vials. And also in terms of working with that, to be able to work with the minimum amounts, the 0.2 milliliters. So an additional aspect is, how do you minimize dead volume? How do you minimize the amount of material needed to initially wet or stimulate the sensor? So this allows the like 1 milliliter of material to be used to do the 4 pulls of about 0.2 milliliters each. So various efforts made to work toward small volumes and accurately sample very, very small amounts of material. So we've talked about 787. I've also mentioned 1787. What are those about, and are they different some way? Well, yeah, they are quite different, really, because 787 functions as a test. 1787, 1787, is an informative chapter. In the USP, anything over the value of 1,000 as a chapter is informative. It's counseling. It's good advice. It's background material on a particular method. So we have, as a companion to 787, very recently introduced the 1787 chapter, which has quite a good bit of information. 787 was effective in August of 2014, and it's basically normative, or demand for dealing, a method dealing with the information needed for proteins, sets out the method and the limits. 1787 is now published, and it has an effective date of May 2015, so fairly soon, and it is listed as informative. Okay, so it is something that's suggested. You don't have to do this, but there's a lot of good information, in fact, in that chapter. So it looks at various measurements for proteins, discusses a whole range of technologies, and describes those and compares them with methods and purposes. So there's different concerns sometimes when you look at protein for research, development, and production, all need different maybe methodologies. And so those are touched on in this discussion of proteins and analyzing them for counting and for characterization of particles. So a very worthwhile chapter. Well, what are some of those methods, and what could be used to help analyze material under 787 in parallel to it, or for other purposes, maybe for some research purposes where 787 doesn't really apply. 787, as is 788, is really focused to a final dose form. But often people use that as a guideline in the research and development side. So 1787 talks about an additional aspect, and you'll start to see this, I think, more in regulatory world, that the collection of data outside of the typical 10 and 25 micron data is recommended for proteins. Okay, again, this is focused towards proteins. So collection of data in the 2 to 10 micron range is recommended, not demanded, so it's not a requirement, but it's recommended. And so they talk about, what about 2 to 5 and maybe 5 to 10? Those might be suggestible ranges to look at, in addition to what you acquire for information in 10 and 25. And in the summary, it talks about, how to use maybe the information you're already getting doing the compendial method, the 787 method, to kind of have a additional insight into the production consistency. Proteins can often be much more difficult to have consistent production, and so maybe different windows into that could be used. So in 1787, it speaks about the correlation of counts of particles from the oligomers through through the 25 micron size, assessed as part of the compendial method. And it may make it possible to rely on the LO, that's light obscuration, determination alone to reveal changes and trends in manufacturing. So it says use this information you're already acquiring and kind of use it to maybe not just pass the test, but maybe to, in a sense, give a sense of the heartbeat of the method. Is it consistent from one week to the next? In this situation, overall control strategy would be used to establish action limits for particles greater than 10 microns, which when exceeded would trigger an investigation, including the characterization methods discussed in this chapter. So it's saying, the information could point to other aspects of production or process control, and they are encouraging, and again, 1787 is recommendation only, encouraging looking and using that data, maybe even thinking about alert or action limits based on some of that to look at the process. And so it also speaks about some of the difficulties with certain formulations in the protein world, even in the small molecule world, but certainly in the protein world. And it says the LO, the light obscuration method, has some technical limitations when used for analyzing certain protein types. And often they change shape. And under pressure, under vacuum, with certain temperatures, proteins are much more inconsistent, you could say, through the analytical process. So what can you do as an alternate method? Well, certainly one very consistent method that's been in place for, again, decades is the Coulter counter method. And I want to briefly introduce you to that as we finish up this discussion. One of the aspects of a lot of proteinaceous solutions, suspensions really, is that they are, the material is semi-transparent. It's almost a majority water, you could say, and in a fluid that is often aqueous or near aqueous. And so the difference, the contrast, the refractive indice, if we're talking about the terminology you could use in the optical world, is very, very limited. The contrast, the ability to see it, it's kind of like seeing something gray in a fog. So we don't really have a perfect substitute for a protein material. NIST and other groups are working on calibration materials, but we really don't have anything that effectively represents that. We have our very accurate spheres that we have, but those, again, don't quite look like proteins, and they have different refractive indices. So what could we do? We have, again, this need to distinguish those, and as an optical response, it's again, dependent on having a good contrast to that. So in 787, it speaks about alternative analytical methods and with adequately developed subvisible particle limits. Well, what are the other methods? And again, 1787 discusses that, and in this chapter it points to alternate or orthogonal methods for investigating the quantity, the enumeration of particles in a solution. So light obscuration, as we mentioned, starts around 1 micron. The Coulter counter has a wider range based, though, on using different orifices in it, but it has a wide range. And again, it's an old method in the sense of history. It's developed in the 1940s and certainly has been effective in analyzing liquids, in the last now, 60 years. And it has capability of looking through the range of visible, subvisible, and submicron with different orifices used in it. It could test per container limits at 10 and 25 microns, certainly, and it avoids, because it is a different method, using a electrical flow method as opposed to an optical method. So the transparency of the bodies that you might run into, be they proteins or something else in the fluid, no longer present an issue of refractive indices. So basically, it's something that will count and size entities in a fluid, and it does this basically by moving the object as part of fluid flow through an orifice. As that object moves through the orifice, it constrains an electric current flow. The electric current flow is set up in the medium, and ions basically move from from the anode to cathode in this design. And if you interrupt that by putting a chunk of material in between through that small orifice, that's something that in terms of the flow of current can be detected. So we can get input back as particles move through that opening because it constricts or restricts the current flow. So that gives us an electronic pulse. Now that pulse is something slightly different from what you get then from the light obscuration system. And what we're really giving then is an equivalent volume. And of course, from a volume, you can determine, in a spherical representation, determine a diameter. So we can go ahead and use that equivalent volume to tell us also then the size of the object. But we have or avoid the issue of transparency or near transparency of the object that you do when you have any optical methodology. So the Coulter method, and this is a comment from one of the posters in a protein congress. The key advantage of the MS4, which is the Coulter counter design model, is its ability to detect particles that are undetectable by light-based MFI, which is a imaging technique, and HIAC, since detection does not rely on the optical properties of the solution or the particles. So another key advantage is that the MS4 can more accurately measure the volume of asymmetrical particles. And that can be useful information. The volume can be very helpful. You could look at the differences between a long, elongated object or oval object versus something spherical versus something that is totally irregular. So it has some more information to give you about objects in a fluid. And it covers quite a wide range and can go down into the nanometer range with the same instrument, but using then different orifices, all the way up into the fairly large range, into what, and under the USP terms, they speak about as visible, that is greater than 100 microns. So, again, from the 1787, which is, again, an advisory chapter in the USP, they talk about the information that could be used and gained from light obscuration, because that is the primary method spoken about in 787. Correlation in the counts of particles from oligomers through the 25 micron size, assessed as part of the compendium method, may make it possible to rely on LO determination alone to reveal changes and trends in manufacturing. So again, just repeating that commentary, that information from the method gives you the pass-fails, certainly, so you have the 10 micron, 25 micron limits, but also consider using the information given by the various techniques, by the light obscuration technique, to help as a process control reflection in developing protein-based materials. So, kind of final summary then. The USP 787 was effective as of the 1st of August in 2014. It is specific to protein-based therapeutics, so you cannot use it for other types of materials, only for protein-based therapeutics. It does exclude vacuums or a material that's delivered through some form of a final filter as part of the, let's say, the hypodermic structure might have a filter in it. Then you would not be, it would be not a demand to use 787. The Hayek 9703 as a light obscuration-based system can satisfy those requirements, and within the software there's various methods to create procedures that can be very useful for looking at the protein-based materials. The Coulter counter is an alternate technology, and it has the ability to work with higher concentrations and to ignore the transparency. However, it does require a presence of ions either naturally in the material or in addition as, let's say, a bit of salt or similar addition into the solution. Sometimes that can be a drawback. It's sometimes difficult to have a consistent, a material consistent when you add anything to it. So if you add extra buffer to a therapeutic dose, you'll find often it changes it. The proteins that might be in aggregate form dissociate, or other aspects that resolve or reverse. So you have to consider anytime you change material by diluting, by adding ions, anything like this, you have to consider, is it changing the material that I intended to look at in executing the method. So with that, I want to wrap up this introduction to the 787 and 1787, and I appreciate your spending time today, and if you have questions, certainly I would encourage you to look at www.particle.com for more information on both of these methods and on 787 in general. And certainly feel free to contact me if you have questions later on. And with that, Judy, I'll turn it back to you.
Thank you for that informative presentation. Before we get started on the question and answer session, I'd like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can. And our first question is, how can accuracy be shown within a method validation for a protein-based formulation?
Well, accuracy, I'm going to guess, relates to accuracy in counts. The accuracy could have different meanings there, I think. And generally, again, you would use a calibration methodology. We don't have something that emulates proteins perfectly today. Again, there are national bodies working on that. But at the moment, we have somewhat of a surrogate in the type of either polystyrene beads or glass beads to represent a spherical object. Unfortunately, most proteins aren't spherical. So I'm not sure exactly in the question what accuracy is going for, but I'm thinking probably we're talking count, and we do have count standards based on spherical material.
Here's your next one. Should stir bars be used to agitate the sample?
I would not recommend that. Again, that would be something maybe to determine. The stir bar could have two negative effects. One can be certainly that it changes the material in the sample because of the movement, because of the agitation. The second problem can be that again, with proteins specifically, that they will tend to aggregate more readily when you introduce a lot of energy into the suspension. And also, should there be any ferrous material, assuming it's a magnetic type of stir bar, it would be attracted to the bar and therefore never be drawn into the sample. And so you would not see metal particles that have a ferrous content, they would be drawn to the stir bar and never be drawn up into the instrument. So you could get a bit of a misleading sample. Generally, we avoid stir bars just because they're difficult to keep clean and to make sure they don't introduce contamination and or affect the process of sampling.
All right. Suppose the drug product is a vial containing a lyophilized protein that is diluted in an IV bag prior to administration. What then are the allowed limits of particles for A, the drug product vial, and B, the infusion bag containing the admixed drug product? And lastly, is the IV bag considered to be a large volume drug product?
The general counsel dealing with lyophilized material is that it needs to be reconstituted and presented in the final form as it would be presented to the patient. So this is kind of the leading direction of that, and it makes it a little bit more difficult. First off, any lyophilized material has to be reconstituted using whatever normally a physician or nurse would do for the process. So if it's going to go into a bag, then basically you need to simulate or emulate that whole process. And again, the focus with 787, one of the reasons they put this container limit in there, is that they're trying to see the dosage that would be given in total in a therapeutic step. So I would understand this, and I'm not on the expert committee, but I would understand this to demand that you would reconstitute it, introduce it into the IV bag, and test the complete ensemble. That's a little bit difficult in the sense that there are different IV bags out there and different solutions, so it's hard to make that an absolute consistent framework. But I think that's no more of a problem than to say, well, if I'm going to dilute any material using my the clean water in my lab, well, in fact, clean water is slightly different from one lab to another, even maybe one day to another. In that. So I'm not sure that's really a strong case against this. But again, the intention for the analysis is to see what the patient's body is going to see.
Okay. When do you expect to have the 787 report updated in the software for the 9703 Plus?
I believe that will be out later this month in April. I'm not 100% sure of that. I know it's imminent and it's just going through its final verification and release. So I would say within the next 30 days.
Okay, thank you. Are light obscuration instruments destructive, and can you collect effluent and perform another test on the sample?
Generally, it's considered destructive. You could collect it. The problem is, especially with proteins, you've now pulled it through the syringe drive, and you've created shear forces, and potentially have maybe associated it with the previous sample. So it's very difficult to recover. And it depends on the type of test, I guess, that would be succeeding it, as to whether or not it would affect the sample. But certainly you have to consider, does any of the method of drawing the sample, moving it through the various tubing, most of which is inert chemically, but still provides a certain amount of shear force and pressurization as you push the sample out of the syringe after it's been pulled into it, and that may affect certain types of materials. So you need to do any further analysis with all that in mind. Certainly probably a simple chemical analysis could be done, but a lot of other things you need to be very mindful of the fact that the device causes a certain expansion and compression, and that might affect the inherent qualities of a protein.
Can 787 apply to a protein solution used as eye drops that have to meet 789 specs?
I don't think so. I haven't thought about this, but generally the focus on 787 is as an injectable. So eye drops, in other words, not an injection, but eye drops, would seem to be outside of that. And so you wouldn't be able to apply it as I would interpret it, even if it was a eye drop that was, again, protein-based. I think the focus would be limited to injectables, but it's an interesting question. I hadn't really thought of that aspect up to this time.
Okay, we have time for one more question. Is the HYAC compatible with organic solvents?
In most cases, yes. Most of the wedded components are immune to solvents, that's stainless steel and Teflon and glass. It would be good to know the exact solvent. There are a couple of O-rings that can be tuned, if you would say, or chosen particular materials to resist certain organic solvents. So it's a good technical question. The important thing would be knowing exactly the solvent used, because there could be a couple of choices, Calres versus Viton, for example, as materials to provide maximum resistance to an organic solvent.
Thank you, Joe. I would like to thank our sponsor, Beckman Coulter, for making today's educational webcast possible. Today's webcast will be available for on-demand viewing through October 2015, October 8th, 2015. The slides are available to download as a PDF. You'll receive an email from LabRoots alerting you when this webcast will be available for replay, and we invite you to forward that announcement to your colleagues who may have missed today's live event. See you next time. Bye.